Hello friends, in this video I will discuss the Schrodinger equation, which is an important topic of quantum mechanics, and I will discuss the matter waves, the wave function, and the time dependent and time independent Schrodinger wave equation. So what are matter waves? So there was a scientist, Louis de Broglie, a French scientist, and in French it is pronounced as de Broglie, but we will pronounce here de Broglie. So according to de Broglie or de Broglie, a wave is associated with each moving particle, which is called the matter wave or de Broglie wave. So he got this idea that if the light wave have the particle nature, then also the particle should have the wave nature. So he gave this hypothesis in 1923, and the wavelength for the particle waves or the matter waves is given by this formula lambda equal to h by p or h by mb, where h is the Planck's constant, that is 6.63 in 10 to the power minus 34 joule second, and this lambda is known as the de Broglie wavelength, and this wavelength lambda depends on the momentum, not on the physical size of the particle. And this was theoretical hypothesis, and it was experimentally verified by Davison and Germer after few years, and this experiment we will discuss in next slide. Now we discuss the Davison and Germer experiment, and Davison and Germer experiment proved the wave nature of electrons in 1927, and it also proved the de Broglie waves, and they observed the diffraction of electron beam incident on a nickel crystal, and they did not try to verify the de Broglie hypothesis, but this was an accidental experiment. There was some problem of moisture in the nickel foil, and when they heated the nickel foil, the atoms got arranged and electron beam got deflected from this nickel foil. So this is the experimental arrangement. In a vacuum chamber, there is an electron gun or filament and one accelerating plate, and there is nickel foil or nickel target, and there is a detector which can detect these electrons. So when this tungsten filament is heated, there are the electrons are there due to the thermionic emission, and they are accelerated using the uh, accelerating plates towards the crystal, this nickel target, and the target is nickel crystal which can be rotated, and there was some detector which we can move, and they found the scattered electrons from the nickel target at certain angle theta, and they found that when the detector was moved, the current was measured, and it was the intensity of the diffracted beams or electrons, and the intensity of the scattered electrons was not continuous, means when we are increasing the voltage, the current should increase like this, but they found the curve like this at different voltages, suppose 44 volt, 54 volt, 64 volt, 68 volt, and there is maximum diffraction at 54 volt. There is maximum scattering at a angle of 50 degree. Here in this image we can see, and this maximum is indication of that electrons are being diffracted at angle 50 degree, and the voltage is 54 volt, and they analyze this using the this Bragg's law, because the crystal is treated as a diffraction grating, and the interatomic spacing between two planes is for the nickel crystal D equal to 0.91 angstrom, and the theta, this value was 50 degree, so the incident angle was 65 degree. If we uh, use this 90 degree minus 25 degree, it will give us 65 degree. So using the diffraction condition, or it is known as the Bragg's law, 2d sin theta equal to n lambda, and for n equal to 1 means first order diffraction, lambda equal to 2d sin theta, 2 into d is 0.91 angstrom into sine 65 degree, and it comes 1.65 angstrom. And they use the de Broglie wavelength using the formula lambda equal to h by p, or p equal to under root 2m E, and E is electron volt because it was maximum for 54 volts, so they use here 12.27 divided by under root B, and it comes around 1.66 angstrom. So these both values are matching. This is using the diffraction equation, and this is using the de Broglie matter waves wavelength. So these both are matching. So therefore Davison and Germer experiment uh, gives the proof that electrons have the diffraction property, and that's why electron can be treated as a wave. Before that it was treated only as particles. So Davison Germer experiment is an experimental proof for the matter waves. Now we will see what is the wave function for matter waves. As we have seen that according to de Broglie, every moving particle should be associated with the wave, and Schrodinger introduced a mathematical function psi for the moving particle, which is known as the wave function, and it is function of space and time coordinates x, y, z, and t, and it is a variable quantity associated with the moving particle, and wave function is used in the Schrodinger wave equation. What is the physical significance of wave function? Psi, the wave function, does not give much information about the particle, but psi square, magnitude of psi square means psi into psi star, where psi star is the complex conjugate of psi. It gives the probability of finding the particle in the state psi, and it is the measure of probability density, and the probability of finding the particle in volume d tau or dv equal to dx dy dz is given by magnitude of psi square dx dy dz, and probability of finding the particle in the space means from minus infinity to plus infinity, probability of finding this in space is 1, and wave function psi satisfying this requirement is known as normalized, and probability of not finding the particle in the space is 0. Then we can say that this um, integral volume integral of this psi square d tau equal to 0. Now what are the properties of wave function? So wave function must fulfill these properties. It should be finite everywhere, and psi should be finite or 0 at any point, and it must be single valued because psi cannot have two values, and if psi have two values means we will have two probability of same particle state. That is not possible, and it must be continuous. This wave function should be continuous. In Schrodinger equation, d to psi by dx square must be finite everywhere, and wave function must be normalizable. So there are basically four properties. It should be finite, single valued, continuous, and normalizable. Now we will understand what is Schrodinger wave equation. So Schrodinger gave a wave equation that is the basic equation of motion of matter waves. Like Newton's law are basic laws for the particles or bodies. So Schrodinger wave equation is basic equation for matter waves, and it is a second order partial differential equation which describes the dynamics of quantum mechanical system using the wave function. And there are two forms of Schrodinger wave equation. One is time dependent and one is time independent wave equation. So first we discuss the time dependent Schrodinger wave equation. The wave function psi for a particle moving freely in x direction is given by this wave function psi equal to a e raised to power minus I omega t minus x by b. So it is a complex wave function where this omega is 2 pi nu and b is nu into lambda. And if we put these values here, the wave function psi will be a e raised to power I minus I omega equal to 2 pi nu, we can take inside this bracket nu into t minus nu into x divided by b. In place of b we can write nu into lambda, and nu will be cancelled out, so it will be psi equal to a e raised to power minus 2 pi I, this nu into t minus this b, nu and nu cancelled out, x by lambda. But we was to get this psi function in terms of energy and momentum p by using this formula E equal to h nu, or we can write it 2 pi into h cut or h bar nu, and lambda equal to 2 pi h bar by p, where h bar is h by 2 pi. So we will write this equation and this wave function in terms of E and p, and we will have this kind of relation psi equal to a e raised to power minus I by h bar et minus px. So this is the wave function, and differentiating this equation with respect to x two times. So first we will have find d psi by dx, so it will be a e raised to power something e raised to power x, the differentiation is e raised to power x, and then we have to take differentiation of this function also. So psi will be d psi by dx will be a e raised to power minus I by h bar et minus px into differentiation of this et, it will give 0, minus px will give minus p, and again if we differentiate one more time, then it will be p square minus p square by h bar square, and I it will give I square, that is minus 1 psi. So from here we can find out p square psi will be minus h square into delta 2 psi by delta x square. Again if we differentiate this equation with respect to t one time or once, then delta psi by delta t. Now this time we have to differentiate with respect to t. So again it will be a e raised to power minus I by h et minus px uh, into differentiation of this function. So px will give 0, partial differentiation, we are differentiating with respect to t, so x will give 0, then we will have minus I into e, so minus I e by h bar into psi, or from here we can find out e psi equal to minus h by I delta psi by delta t. So we need these p square psi and e psi terms so that we can get the final Schrodinger equation using the energy function. So we should remember these p square psi and e psi terms in terms of this delta 2 psi by delta x square and delta psi by delta. For a particle which is moving with very low speeds as compared to light, then the total energy E is the kinetic energy plus potential energy, and kinetic energy is p square by 2m plus potential energy is u, and if we multiply both sides by with psi, E psi will be p square psi by 2m plus u psi, and in last slide we have calculated E psi and p square psi and put these values in equation number 8, or this equation, energy equation, and then we have E psi as I h bar delta psi by delta t, and in terms of p square psi we have minus h square h bar square by 2m delta 2 psi by delta x square plus u psi, or we can write it as minus h bar square by 2m delta 2 psi by delta x square plus u psi equal to I h bar delta psi by delta t. So this equation is known as the time dependent Schrodinger wave equation. And if we can write this equation in operator form, h this cap psi equal to e cap psi, or h operator psi equal to e operator psi. This symbol here is known as the operator, and this h operator is known as Hamiltonian operator. This means energy operator minus h square by 2m. Del square means it is delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square. This is del square is also known as the Laplacian operator, and this e operator, energy operator, is I h delta by delta t. So these are the operators in quantum mechanics. So h is known as Hamiltonian operator and e is the energy operator. And in three-dimension form, the time dependent equation will be uh, I h delta psi by delta t minus h square by 2m. Now we will also take the y and z terms also, delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square plus u psi. So this term is known as del square or Laplacian operator. Now we can find out also time independent or the steady state form of the Schrodinger wave equation. And the potential energy in most cases does not depend on the time. It varies with the position of the particle only. So then we can take the equation by removing all the terms which have t in that wave function, and if we have the wave function for a free particle like this, psi equal to a e raised to power minus I by h bar et minus px. This we have used earlier. So now we have this wave function as psi equal to a e raised to power minus I by h bar et minus px, and we can separate the time and position x terms separately, and we can write this a with the position term as psi, normal psi. Here it is bold psi, e raised to power minus I e by h bar t. This is the time term is there, and if we put this value in the time dependent equation, time dependent equation was I h bar delta psi by delta t equal to minus h square h bar square by 2m delta 2 psi by delta x square plus u psi. And if we put the value here, psi equal to psi e raised to power minus I by h bar t, so we differentiate with respect to time, so we will get I h psi e raised to power minus this into differentiation of this with respect to t, it will give minus I e by h bar. Similarly, here we can write with respect to x, so there is no t term, so it will be minus h square by 2m psi e raised to power minus I e by h t delta 2 psi by delta x square. It will be here u into this psi, we can put psi e raised to power minus I e by h bar t, and if we rearrange the terms, and some terms will be cancelled out, and finally we will get equation like this, delta 2 psi by delta x square plus 2m by h bar square e minus u psi equal to 0. Then this equation number 3 is known as the steady state form of the Schrodinger equation. And for a free particle, this potential energy u or v equal to 0. So equation, and this last equation becomes delta 2 psi by delta x square plus 2m e by h square h bar square psi equal to 0. This is the steady state form of the Schrodinger equation for free particle. And in three-dimension case, just we will have to, this is for only one dimension, x dimension, x axis, so we will also take delta 2y by delta y square plus delta 2 psi by delta z square plus 2m by h bar square e minus u psi equal to 0. So this is the Schrodinger wave equation for three-dimension case, or we can write this term as del square also, del square psi plus 2m by h bar square e minus u psi equal to 0. Now we will discuss the eigenvalues and eigenfunctions. The value of En for which the Schrodinger equation can be solved are called eigenvalues, and the corresponding wave function psi is known as eigenfunction. Suppose this kind of, we have a function psi and we have a operator q, and if this operator operates this function psi, then we have the function and some coefficient. This coefficient is known as eigenvalues and this psi is known as eigenfunction. So if we take one example, uh, for operator is g2 by dx square and psi equal to e raised to power 2x. So find the corresponding eigenvalues. So if this where operator is d square by dx square of function psi psi n is equal to e raised to power 2x, and we have to differentiate it two times. We will get first e raised to power 2x into 2, then again 2 into 2 into e raised to power x 2x, so it will give 4 e raised to power 2x, and e raised to power 2x equal to psi. If we put 4 into psi, and this 4 will 4 is the eigenvalue, 4 is the eigenvalue, and psi e raised to power 2x is eigenfunction. There is one more term that is known as expectation value or the average value of any quantity. Fr is defined as this symbol Fr equal to psi star Fr psi d tau. And for a position vector R, if we want to get the expectation value or the average value equal to psi star R psi d tau. And for the momentum operator, if we are taking P operator equal to h by I del, or if we are taking it in x direction only, I minus I h bar delta by delta x. So expectation value of P will be minus I h delta star psi star delta psi by delta x d tau. So this is the how we can find out the expectation value for a given function Fr. Now we see one example. We have to calculate the expectation value of P for the wave function, which is defined as psi x equal to under root 2 by L sin pi x by L for x 0 to L, and it is 0 for x greater than L. So expectation value we denote by this symbol, and P psi star P psi d tau, and P is the operator h by delta x if we are taking only x component. So psi star h by I delta psi by delta x dx, and from 0 to L psi equal to defined as with this function under root 2 by L sin pi x by L, it is given. So if we put the values here, psi star means this is the complex conjugate of this function, so it is a real function, so psi star will be psi. Psi star will be like this, and if we h by I by delta x of psi under root 2 by L sin and sin pi x by L, so it will be sin pi x by L into differentiation of this cos pi x by L, and also there will be terms like pi by L, and this under root 2 by L will give 2 by L, and finally if we differentiate integrate sin uh, 2 pi x by L, we write sin 2 into sin x cos x, we can write sin 2x. Like similarly sin 2 pi x by L here, and we integrate this function sin x, so minus cos x by this 2 pi x by L will give 2 pi by L, and if we put the limits, finally we will get cos 2 pi minus cos 0, and cos 2 pi is 1 and cos 0 is 1, so 1 minus 1 is so expectation value of P equal to 0. So here are some important operators in quantum mechanics. Suppose momentum operator, it is denoted by this kind of symbol px, and like this a unit vector symbol is here, but this is operator here px cap equal to minus I h bar delta by delta x. So this is momentum operator. Also one kinetic energy operator is there, minus h bar square by 2m delta square by delta x square, and also one important operator, that is energy operator or Hamiltonian operator h cap capital H cap, and minus it is minus h bar square by 2m delta square by delta x square plus b. So this is kinetic energy plus potential energy. Thanks for watching this video, and if you are new to this channel then please subscribe, and if you have any queries or suggestions then please write in the comment box. Thank you very much.